In this section, we will first learn how electronic configuration influences trends in atomic radius, ionization energy, and electron affinity. Later in this section, we will discuss chemical bonding concepts. Periodic trends in atomic radius, given here in angstrom units. Atomic radius increases down a group or a column in the periodic table. If we examine group 1A elements, we see that the radius increases as we go from lithium to cesium. This is due to the fact that as we go from lithium to cesium, the principal quantum number increases, which increases the distance of the outermost electrons from the nucleus, resulting in increased atomic radius. Atomic radius decreases across a period in the periodic table, as shown here for period 2. As we go from lithium to neon in period 2, the effective nuclear charge increases. Therefore, the nucleus is able to exert its full force on outer electrons, thereby contracting the radius. As we go from lithium to neon, we increase the number of protons in the nucleus. With increasing number of protons in the nucleus, the number of outer electrons also increases. However, the electrons sharing the same principal quantum number cannot shield each other from the pull of the nucleus. This increases the effective nuclear charge as we go from lithium to neon in period 2. Periodic trends in ionization energy, given here in electron volts. The first ionization energy of an atom is the energy needed to remove one highest energy electron from the outermost orbital in that atom. The closer an electron is to the nucleus, the more difficult it will be to remove and the higher its ionization energy will be. Therefore, ionization energy increases across the period with decreasing atomic radius, as shown here for period 2. Ionization energy decreases moving down a group with increasing atomic radius. Group 1A elements have low ionization energy since the loss of an electron results in a stable configuration as in noble gases. Example, if you remove the outermost electron, that is the 2s electron, from lithium atom, it would result in lithium ion with noble gas configuration as in helium. Also, as we go down a column, the nucleus has less hold on the outermost electron. Hence, the ionization energy decreases down a column. Periodic trends in electron affinity, given here in kilojoules per mole. Electron affinity is the energy change that occurs when an electron is added to the highest energy orbital of an atom. Generally, electron affinity increases across a period. Group 7A elements have some of the highest electron affinity because of their ability to form stable anions by adding an electron. Example, When we add an electron to the group 7A element fluorine, it forms fluoride ion having the same noble gas configuration as in neon. 6A and 7A elements are known as electronegative elements. We will now discuss chemical bonding concepts, starting with ionic bonding in sodium chloride, NaCl. When sodium and chlorine react, sodium transfers its 3s electron to the 3p orbital of chlorine. In this process, sodium acquires a positive charge and has a stable electronic configuration as in neon. Chlorine acquires a negative charge and has a stable electronic configuration as in argon. The stability of Na plus and Cl minus ions due to their noble gas configuration contribute to their ease of formation. The electrostatic attractive forces between the oppositely charged ions Na plus and Cl minus results in an ionic bond between them. The above reaction is an energetically favorable exothermic reaction as steps below show. Ionization energy of sodium is equal to plus 502.0 kilojoules per mole. Electron affinity of chlorine is equal to negative 349.0 kilojoules per mole. Electrostatic attractive forces between sodium and chlorine ions is equal to negative 552.0 kilojoules per mole. The net energy is a negative 399.0 kilojoules per mole. The low ionization energy of sodium and high electron affinity of chlorine favor the above reaction. We will now discuss covalent bonding concepts, beginning with Lewis covalent bond model. We know that ionic bonding occurs between atoms that have significant electronegativity difference. Covalent bonding occurs between atoms that have the same electronegativity, for example, between hydrogen atoms in a hydrogen molecule, or between atoms of similar electronegativity, for example, between hydrogen and carbon, as in CH4, methane. In Lewis model of covalent bonding, the bonding between two hydrogen atoms occurs when they share their 1s valence electrons with each other. In this model, each hydrogen atom, due to sharing a pair of electrons, can be viewed as having an outer electronic configuration like helium, giving it stability. In the Kekulé structure, the two electrons a covalent bond shares is indicated by a line. The covalent bonding in a chlorine molecule can be represented as here, where each chlorine atom shares a pair of electrons. Due to this, each chlorine atom can be viewed as being surrounded by an octet of electrons like in noble gases. This gives stability to the molecule. Both ionic bonding and covalent bonding concepts are based on the octet rule. As per this rule, main group elements, when they bond covalently with each other, share electrons to achieve stable configuration where they have 8 valence electrons as in noble gases. Main group elements may also transfer electrons between them as in ionic bonding to achieve noble gas configuration. The noble gas configuration gives them stability. Electronegativity and polar covalent bonding. The tendency of an atom to draw the electrons in a covalent bond towards itself is referred to as its electronegativity. Fluorine is the most electronegative element in the periodic table and has an electronegativity of 4 in the Pauling scale, an arbitrary scale. Alkali metals in group 1A are the least electronegative elements. They are called electropositive elements. They have a tendency to donate electrons. Electronegativity increases across the period and decreases down a column. Bonding in hydrogen fluoride. The bond between hydrogen and fluorine is a polar covalent bond. Fluorine, due to its inherent attraction for electrons, pulls the bonding electrons towards itself, polarizing the HF bond. This bond polarization is denoted by a delta positive charge on the hydrogen atom and a delta negative charge on the fluorine atom, or by a symbol. Electronegativity difference between the bonding atoms will determine the type of bonding they will form. If the electronegativity difference between the bonding atoms is 0 to 0.4, it will form a covalent bond as in a hydrogen molecule. If the electronegativity difference between the bonding atoms is more than 0.5 but less than 2, it will form a polar covalent bond as in hydrogen fluoride. If the electronegativity difference between the bonding atoms is more than 2, it will form an ionic bond as in lithium fluoride. Molecular orbital theory for explaining bonding in hydrogen molecule. Molecular orbital theory views the bonding in hydrogen molecule as due to the linear combination of two hydrogen atomic orbitals. This mathematical model predicts that the hydrogen atoms can combine in two ways: an additive combination, which decreases the energy of the system to create a bonding molecular orbital, or a subtractive combination, which increases the energy of the system in an antibonding molecular orbital as compared to two separate hydrogen atoms. When the atomic orbitals of hydrogen come together at a particular distance corresponding to their bond length, the additive overlap results in the two nuclei and the two electrons going into a molecular orbital. This releases 105 kilocalories per mole energy, equivalent to the bond energy of a hydrogen molecule. The molecular orbital encompasses two nuclei and two electrons. Molecular orbitals, like atomic orbitals, have specific shapes, volume, and energies. Basic rules of molecular orbital theory. 1. Electrons enter the lowest energy orbital available. 2. The number of molecular orbitals is equal to the number of atomic orbitals combined. 3. Any molecular orbital, just like an atomic orbital, cannot have more than 2 electrons. When they have 2 electrons, they must be paired or have opposite spins.